what's going to happen now, I'm going to go through a bit the algorithm and starter code, and then I'm going to show you some of the code for it, and then you're going to get some time to code it yourself. So what is it like? The Q-learning algorithm is like, so you kind of have step size, it's between 0 and 1, it can be like 0.01, I think I have it as a default. And then you have some kind of epsilon, also going to be like 0.01. And then you say QSA, initialize it for each state and for each action. So this is like a Q table that has all state action combinations stored in there. And we can set everything arbitrary, and we set the terminal 1, we set all the terminal scores to 0. If it's like terminal state. And I think I initialized them all empty, I believe. And we're going to see it in the code. I all initialized them with 0 and not with like a random value. And we're going to initialize the game, and then play the game. You play one episode of the game. So you start a game and you just play until the termination criteria of the game has been reached. And what you do, we just have an epsilon greedy. When we play the game, we choose our action based on the epsilon greedy policy, which means with a certain probability of epsilon, we do a random action, else we take the action with the highest state function, with the highest value, the highest Q value. And then we take the actions, and we get a reward in our next state, and then we update the estimate, just as we discussed earlier, and then we go into the next state, and then we just continue. And we do it like how many times until we are finished, and we don't care. Any questions?
And how do we place the value for gamma over here?
This gamma is the like the future discount. It can be 0.9, 0.98. It's another hyperparameter. So gamma, alpha, epsilon, these are all hyperparameters, but most of the time they're not super sensitive.
So just one question, like say for instance, once all of these things are coded, right?
Yeah.
So what's the decision post that when you say for instance, if you're putting it to a different environment, the formula stays the same. So what are you really changing once you're actually doing stuff?
If you mean for different environments?
For different environments, say for instance, we've got Q-learning, we've got other things that we did last time around. So once they're coded, effectively the only thing that we have in our ability to change are just epsilon, alpha, and gamma, right? There's nothing else that we can change.
Yeah, for Q-learning, there's nothing changed. Nothing.
So what do we do then? Like we just randomly just put alpha and just wait for it to do it, or is there anything else that we contribute to it?
So later we're going to do deep Q-learning,
okay.
So where you actually change the neural network architecture, where you can do things.
Mm-hmm.
Like if you want to optimize these parameters, a good way of optimizing any hyperparameter is like a Bayesian optimization technique, and then you have some kind of loss function you want to optimize against, and you just randomly sample your hyperparameters, and then you optimize them against whatever you want.
Sorry. Could you walk us through that equation once more? So you have a QSA.
So we have our.
I think I just want to point out where I think most of my question is. So you have you're just updating your state action value, right, your Q value.
Yeah.
And the right side of the equation, you have some reward plus some gamma, discounting the term. That term is, I think, most of my question. You have a small a and a big A. That QSA is just the previous one. I think what my questions are, what's the point of subtraction over there?
So if you remember before, we had the TD error. Mm-hmm. So this is kind of my better estimate of the state function of the QSA, and this is my current QSA. So I choose an action from a state with epsilon greedy, right? And for each action state, I have this Q matrix. At the beginning, it's 0, right? So it's going to be here, this value minus 0, right? And then I have like a future state, right? So I take from all the future state, I take all estimates from all possible actions, and I take the maximum value of it, and I multiply it with gamma, so kind of my expected future reward. And then I have it with my reward. So all these values at the beginning they're gonna be 0, right? All three here. This is gonna be 0, this is gonna be 0, this is gonna be 0. So for the very, very first step, it's gonna be alpha times r. So for the very first attempt, I just have my learning rate and my immediate reward. And then as the game continues, I always look a lot ahead. Because see, I play this game one time, right? Now I have selected some action, right, for the next state. So the max SA, if they have a constant reward for every step, say every step I make 1 point, right? So after the first round, I'm gonna be alpha R, and then my maximum estimation from the next step is gonna be also alpha R, right? For any step that gives me any reward, right? If all the rewards, all the steps that let me die, then I get neurons. And of course I'm gonna take greedy reward for this one.
So I think the point of that subtraction is if that max value was greater than your previous Q value, you got to add to that Q value. Is that correct?
I think what the confusion is here. So you first choose, you start with that A, the lowercase a. So you examine all the possible actions. When you, if it's epsilon greedy, you end up choosing one action. When you've chosen it, then the A, that capital A would be equal to that A. That's the action. Then you subtract whatever Q that state action value has. That state action pair has.
No, but that A, small a is for the next step, it's not for this one. No?
Yeah, small a is for next step. So basically, you have new information coming, right? And you have a estimate right now. The new information is like the reward that you get and the estimated reward of your next state, the summation of these two, right? So you subtract that from your current value. That's the new information minus the current value.
So
that's
if
the difference.
If it's greater, then you get a positive value.
If it's negative, you get negative.
Exactly.
And then
you subtract it
multiply
from the
to some-
value function, right?
You can think of it
Just like the error, right?
It's error. It's kind of, you can think of it like averaging over it, right? With step size over. You average it over it, right? So you do it one time, you get some estimate and do it again, and then with alpha times your next estimate, you add it to the next one. You take the average of size
The
alpha.
key thing here is like your new information is that, okay, I took this step and this is the reward that I get, immediate reward. And now I'm in a different state, and that state has its own estimated reward, right? Which is Q, S prime A. And it's not,
I think
you need to
just
take
move-
max because like there's a possibilities of going to different places from there. You need to take the max.
Yeah, it's okay. I think we just move on to the implementation part. So this is maybe is going to help you clarify a few things. So let's see here. Can you read it? Let me see. Can you read it? Is it readable? Okay, so you're gonna play a game, and you start here, over here, and this is your goal. And each time you take a step, there's like some wind blowing you down with a certain probability. Each time you take a step, you get like -1 point, and if you fall off the cliff, you get -100 points. Well, I think there's no wind actually. There's no wind. You start here. You need to go here. Each step you get -1, and if you fall off the cliff, you make -100. So this is if you're here and you go down, you're gonna make -100. And that's the Q-learning algorithm. And here is implementation for Q-learning. And so this is kind of the gamma, the discount factor. This is our alpha. This is the epsilon. This is like how many times do I play the game? I'm gonna play the game like 10,000 times. Or not 10,000 times.
One question from online. How do we initialize Q and R?
What's Q and R?
Q and R is our reward.
What is the reward?
The reward R, Q is the Q in the
the reward we get from the environment. I don't know what he means with Q and R.
Does it mean that like how we initialize the value function?
You mean QSA?
QSA, okay.
There's no Q in R. Anyway, let's move on. And let me see. So this is basically our greedy policy, which we can get by applying like a greedy function on our Q table. And this is our Q table, which is like empty. Like when you initialize the class, you're going to init with an environment, and it's kind of like a state times action table. And this is like the core function you're going to implement. I'm going to talk a little bit about this, and then I'm going to show you a little about the helper functions I have, so you kind of understand how the class works. So I guess the input, it takes kind of like a state, an action, and environment. This is like the TD update. So this is exactly this step here. This is the TD update, which we have to do. You have to code. And what you say, okay, I do a step of the environment, I get my next state, get my reward, and have my action, right? And then we say, okay, what's the best next action? So you just get the best action in the next state. And then we say, okay, this is our TD target, that's the one inside the brackets. And then the TD delta is like the whole thing. And then this is how you do the update. And that's it. And say if you initialize the object, you initialize the model, you give it an environment, and what it does, it just make a dictionary, which is the n times m. So say with here q self q of s of a returns the q value for a state s and action a, and self q from s returns all action q values for a state s. And then I have a run episode. So what I do for t runs, I count the run, and I say, okay, I apply like a greedy action, so I get the action probability for every state, and then I just select a random action based on the probability I have for every of these actions for this given state, and then I just update the state by giving the function calling TD update and getting a state and passing the state, the action, and the environment. And this is just like just a greedy policy doing the drawing. And then I get the next state, and if I'm done or not. And if I'm done or I did 50 steps, I just finish the episode and start again. And this is like some helper function. So we say, okay, train. So given giving an environment, we just train on the environment. So what does we split, and E is like the number of episodes. So for the number of episodes, we just we run one episode. And run episode is like what I said, you run the TD function over every step. And these are the policies we have. We have like a greedy policy, which just returns you the best action for giving all the Q values of the function. And then we have an epsilon greedy policy, which basically says we add an epsilon error to all the probabilities of selecting a certain action. So this just basically adds an epsilon error. A heat map we will need later to visualize the performance. So you're gonna be tasked with finishing this one function. Are there any questions? So did anyone get it running?
Okay, hey guys. Before it crashed. Until it crashed.
Until it crashed? That's okay. So everybody, we're gonna continue. We're gonna go through this together. So anyone got a working solution in the end?
Alright, see you guys.
No? Okay, then I'm just gonna say, okay.
I can see happiness in your face. Like, I'm happy that nobody did that. So
why?
Just kidding.
Like, I wish everybody were able to do it. It's either like I didn't explain it. It's most likely I didn't explain it very well. So self.q, right, is the Q table. So I can give it a state, and it gives me all the estimates for all the actions, right? So next state will give me basically all the estimates for the next state, right? It's going to be an array. And I want to know what was the best action, right? So I do np argmax. np argmax gives you the maximum, the argument, like the position with the maximum score. And then we say, okay, what's this target, this gamma minus r reward plus gamma and the maximum reward of the next state, right? So gamma was like self dot df, this counterfactor, and then times
Best next action.
the self dot q, and then we look it up like, so for the next, what's the next state, right? And the best action, so best action, best next action is it. And then we have we want to calculate TD delta, right? So we have the target, TD target is the one we had before, right? So this TD target, and then minus self dot q. We need the current state and the current action, right? So it's going to be state and action. And now we need to do the update, right? So it was going to be like self dot alpha times the error, right? So it's going to be, what was the TD delta? If I remember it correctly, just a second. Yeah. And that's it. So, are there any questions?
I'm still getting an error
What is that?
on the if done or t equals 50.
Yeah, just change the t to bt because he defines the iterator to be bt rather than t.
Oh, it's like a typo.
That's it, yeah.
It should be t. I don't know why it says b there.
I redefined t to be bt. But okay, that was
Are we all working on the same collab?
Yes.
It's two.
So if anyone
It's
changes,
collab too, right?
yeah. But if someone changes the code, it changes the code for everybody, or everybody has its own copy.
on copy.
I think it's
I don't think they can run yours.
You can't.
You can't change it.
Okay.
Where is this should
So this should work now.
you can change because it might make an error.
What
Your
is supposed to
solution
happen?
afterwards. Well, you define the class there, then you have to run the test code. And you should see this. It's half.
And that's what the game looks like. And that's what the policy looks like.
Test run.
Everybody, attention. And that's what the game looks like. The circle are the places where you can start. You can walk on. This is our start position. This is our end position. And the C are the cliffs. And this is like our optimal policy. Or the policy was generated by taking the epsilon greedy for every state. And we see we just go, once we are here, we just go right and then we go down. And that's it. Like 1 is right and 2 is down. And that's the Q values. Like these are value state action value pairs for basically for each state if I walk up, right? And you see, okay, if I take the minimum, I'm just gonna walk here, gonna walk up. Here I'm gonna walk up, and here I'm gonna walk up again. Let's see if this still stays the same. Yeah, so here it doesn't matter, so we're gonna walk right. And then here you see minus 6 is like better than minus 6.8, you just keep walking right.
why are they negative?
Because we take minus 1 point for each step we do. And this is for walking right, so see it's the same. And then for walking down, you see that if you're here in this state and you walk down, you just get minus 100 points, right? If you walk down. So it's going to be a large negative number. And these estimates can be really bad because once you do it once, you never do it again. This is how the Q-learning works, because you see it's going to be a strong negative reward. So you just get a very pure estimate of it. But it's still good enough to know that it's a big negative one. And then for left, it's the same. Let me see. Okay. So, let's see. All right. So is there any questions?
You have the code from the first example.
What do you mean from the?
You showed an example before this.
You mean from last week?
No, this is the one right before when I was asking why they built the wall.
Oh, the
Stanford one.
JS
The
Stanford.
Karapathy visualization on
Ah.
Stanford.
Reactor.js.
This one?
No, like the website you showed us.
Oh, this one?
Maybe I can just get the website.
Reinforce.js.
Oh, you have the slide, right? You have the link. So the slides I have here in the keynote, these are the slides that are in the first session slides. So you have the link to this website. And if you just Google reinforce.js, you will find it immediately. It's called reinforce.js. So it's like a JavaScript for reinforcement learning. Like do this kind of toy things.